Hello everyone, I'm Zhang, a PhD student from Northwestern Polytechnical University, and in this video I will introduce our recent work, V-ORAM, a versatile and adaptive ORAM framework with service transformation for dynamic workloads. And this is a joint work with my supervisor, Professor Helei and Xingliang Yuan from the University of Melbourne, and Zhiwen Yu and Bing Guo. To start with, let's consider a hospital that wants to outsource its medical data. And for security, the hospital will encrypt the data before outsourcing it to the cloud servers, and these servers are usually assumed to be semi-honest. However, encryption alone is not enough for privacy, as the client accesses the encrypted data, and the adversary can observe the access frequency of each ciphertext, and combined with some public informations, adversary can infer the mapping between the ciphertext and the plaintext. And this is called access pattern attacks and has been widely studied in recent years. As a mitigation, oblivious RAM or ORAM can generate random access patterns. For example, if a client outsources n blocks in the server side and want to access the data at index 2, ORAM can convert it into a series of random read and write operations, therefore protect the access patterns. Note that ORAM are stateful and need to maintain the metadata in the server side and the client side. It also has cost lower bound of log n. There is line of work applying ORAM in various scenarios, for example, parallelization, secure computation, and searchable encryption. And these ORAM schemes are typically tailored and optimized for specific workload. However, in practice, the workload of ORAM can be dynamic. And for example, in a hospital with electronic medical record system, during its routine usage, there is no specific performance requirement, while in medical analysis, it may require keyword search and other complex queries like join and aggregate. Or in cloud storage system, the requested distribution during a day may have peaks and off-peaks, and during peaks it requires higher throughput and lower latency. And this dynamic can also be caused by system performance changes, for example, different CPU and bandwidth usage. We find that using unmatched ORAM is not a good option. For example, using a synchronous ORAM in a synchronous network, it could harm the data correctness. And if you're using communication-centric ORAM in low bandwidth, it will downgrade the performance. So it easily comes to our mind that there are two strawman solutions. First of all, we can download and rebuild the entire ORAM, and this will generate massive communication cost. And the second one, we can maintain multiple ORAM instances for different workloads, and but this will multiply the access cost. And both solutions are secure but not efficient enough. So can we handle the dynamic workloads both securely and efficiently? In this paper, we propose a dynamic ORAM framework, V-ORAM, and different from two strawman solutions, V-ORAM can securely transfer between three tree-based ORAMs and only has constant transformation cost. And we propose the ORAM service transformation cost protocol, which is OST, and it mitigates tool leakage during the transformation and also has constant cost. And we also provide a planner to help the user to choose the parameter of ORAM, and please refer to the paper for the planner part. Let me first introduce the basic workflow of our considered ORAM, that is pass ORAM, real ORAM, and conquer ORAM. Pass ORAM maintains data in a binary tree, and where each node contains a bucket with multiple blocks, and each block is mapped to a path, and that is the bucket from a leaf node to the root. And the client maintains a map called position map to record the position of each blocks. And it also maintains a stash for caching the data. And here, for example, if the client wants to access the block 1 that is currently mapped to the path 2, the client reads the blocks on the path 2, shuffles them, and remaps the block to a new random path, which is 0 here, and then writes the block back. And the real RAM, on the other hand, maintains additional dummy blocks in each bucket, and these dummy blocks can be efficiently generated by the client. Similarly, to access block 1, the client reads a single blocks from each bucket in pass 2, and these blocks can either be the block of interest or random dummy blocks. And then the server XOR these blocks and sends the result to the client. Since the client can regenerate the dummy blocks efficiently, and it can then recover the target block using the XOR. And this block is then remapped to the new random path, which is 0, just like the passive RAM. And here, real RAM does not evict the blocks immediately, but after every A curious, which is the predefined parameters. And therefore, we call ORAM like real RAM periodic eviction, and the passive RAM as instant eviction. And we need to remark that once the dummy block is accessed, it becomes invalid and cannot be accessed until next evictions. And their locations on the tree is also private information, and this is important and is related to the leakage during the transformation. And here we omit the workflow of the Conquer ORAM, and but we need to remark that Conquer ORAM is built upon real RAM and also leverage dummy blocks. We choose this ORAM because we first summarize the taxonomy of common workloads, and here the general storage does not require a specific performance and aims to reduce the maintaining cost. And the real-world update workload will requires low latency, and the parameter access workload serve for the multi-clients and have higher throughputs. And in the resource-constrained workload, the client will only has limited storage and cannot store the entire position map. And another workload is specialized functionalities, for example, like keyword search and secure computation, or serve for the asynchronous network. And we find that these three ORAM can cover the most general workloads. So in V-ORAM, we have an honest client and a semi-honest server, and we assume that the adversary can observe all the ciphertexts and their access status. And we also assume that the access within each ORAM is secure and correct. And we also do not consider the attacks that cannot be defeated by the original ORAMs. So how can we design the transformation protocols, as designing protocols for any two arbitrary ORAM is impractical? Instead, we decide to find an intermediate. The intermediate should be compatible to other ORAMs, and it should also be affordable without heavy computation or communication. And we also want it to avoid heavy costs during the transformation. And therefore, we can only design the transformation protocol between the ORAM and this intermediate. And we call this ORAM as base ORAM. And after investigation, we find that real RAM is a good option for the base ORAM. And as shows the figure, it is compatible to other two ORAMs, and it leverages lightweighted XOR computation. And we can also reuse the dummy when switching between the Conquer ORAM. Let me introduce the high-level workflow of the transformation. And when we switching between Conquer ORAM, V-ORAM first inherits the dummy blocks, and therefore we do not need to generate dummy for every transformation. And then we need to download and merge the server-side metadata of the Conquer ORAM. And here we find that if the dummy block is not properly inherited, it will leak the access patterns. And as for the switching between path ORAM, the position map and the stash can be directly inherited. And but what about the dummy blocks, as the path ORAM do not leverage the dummy blocks? And one option is to retrieve all dummy blocks and treat them as real block, and which will definitely increase the cost. And so what we want is to retrieve only the real blocks, but this could leak the position of the dummy blocks. The first leakage is reaccessing the invalid dummies, which can happen when switching between Conquer ORAM. And the figure shows a bucket of ORAM with periodic eviction, for example, the V-ORAM. And it first reads the dummies 3 and updates the status of the dummies in the metadata. And then if we switch to ORAM with also has a periodic eviction, for example, the conquer ORAM, and without previous metadata, and initialize a new metadata, which is all set to valid here. And suppose the new ORAM reads the dummy block 2, and the adversary will learn that this block is the dummy block because only the dummy block is accessed twice, and while the real block will only accessed once. As for the second leakage, exposing the dummies positions, which can happen when switching between path ORAM, the figure shows the bucket of ORAM with periodic evictions, for example, the V-ORAM. And if it switched to ORAM with instant eviction, for example, the path ORAM, and then the new ORAM access only the real blocks, and as we just described. And this will leak all the location of dummy blocks because only the real block is downloaded and the left block is the dummy blocks. And then therefore leaks the access patterns of next ORAM with periodic eviction, for example, the conquer ORAM. Our mitigation is simple. We just need to evict the bucket before the leakage, and we define access limits as the number of secure accesses before eviction. And for ORAM with instant eviction, like path ORAM, the value is 1, and for ORAM with periodic eviction, like V-ORAM, the value is the number of the dummy blocks. And here we maintain a map called the record map, and to record the access limits of the buckets. And we will evict any buckets that reach their access limits, and we call this eviction evicted record. And please see our paper for more details. Let's look about the previous example. And the record map of this current bucket is 2 and 3, since there are 2 out of 3 dummy blocks is invalid. And after switching to an ORAM with instant eviction, for example, the path ORAM, and here the metadata is correctly inherited, and then the record map is updated to 1 and 1, since the access limit of the instant eviction is 1. And after switching to another ORAM with periodic eviction, for example, the conquer ORAM, and this bucket will be evicted according to our rules, and then the new ORAM can securely access all the dummies. Our solution is efficient. Evict record only incurs constant communication and computation cost, and also with linear storage cost. And since V-ORAM do not modify any internal protocols of ORAMs, and its stash size is still O log n blocks, and the transformation cost of V-ORAM is also constant and do not scale with the number of blocks. So we implement a prototype of V-ORAM in Python and thoroughly evaluate it. And we also use some real-world medical dataset as case studies. The transformation cost of V-ORAM is constant, while the 2 Strawman baseline mentioned before has the cost of ON and O log n. And in our evaluation, ORAM can reduce up to 30,000 times of cost, and this factor will grow with more data we store, and the more benefit we will gain. The cost of evict record is also constant. Here we define 3 types of cost, describing the cost of eviction, and their amortized eviction, and is the original cost of ORAMs. And here, evict record only introduce additional processing time of less than 5 milliseconds, and the communication costs of less than 50 kilobytes. Finally, we evaluate V-ORAM on 3 medical datasets, and we first divide the workload into peaks and off-peaks according to the throughput. And we use V-ORAM for peaks and path ORAM for off-peaks. And the result shows that V-ORAM reduce the monetary cost of up to 33%. And however, in some cases, if the parameter is not chosen properly, V-ORAM will increase the cost, and which is the reason why we provide a planner. And we also find that V-ORAM is more suitable for workloads with higher variation. As a conclusion, in this paper we propose a versatile and adaptive ORM framework we call a V-ORAM, which enables secure and efficient ORM transformations, and it is also performs well. And this is the end of this video. If you have any questions, feel free to contact me via my email, and thank you very much for listening.